Another programming structure that we have in high-level language is a force structure. Let me specify the plot in C, or I spoke from 0. I understand. And that's speaks. If they are in a nice place. So let's see the corresponding flowchart of this simple code. So first I have to initialize this with 0. Then the fourth statement, as you know, there are two parts. First, the initialize the context. You can see here, I will be initialized one time. Then we check the condition. Here, the condition is by less than 10, but let me convert it to the I equal to 10 for this example because you didn't know to have this type of condition yet. If I is equal to 10, there are two possible outcomes, yes or no. If the answer is true, then we move to this point and compute the x equal to x plus I. And then we go to the eastern part of the floor, and in this example, add 1 unit to the I. And then we should jump back for this location. So this is the unconditional jump. This is the J in a section. But this part is the conditional jump. According to this condition, we will come to this point. For this point, well, this is the exit or end of the program presented. So this is the flowchart equivalent to a symbol for insurrection. As you can see, there are two parts, one unconditional jump and one branch. So here we have an example. In the high-level language, we write the letter structure with quote statement. So the value of the A index, I will be up with the variable G. It is a scope in the V, then I will be apt to go there. As in all, if I is not equal to the J, we come back and we look. If we execute the A index 1 and the way that we compute A index 1 covered in the previous part. So this is the body of the loop. This is the part that the loop index is changed. I will be at this variable J. Assume that these variables are assigned to these registers, and this is the foundation that we want to check. If they are not equal, then go to this point. This is the implementation of the previous code. This is the part that we compute the index. I read it, then added with the in this point we only compute the index and then we load it in register 24, and that index 1 will be at the G and register 17. So the comment part of the issue section completely shows us that what is the actual output for each part. Then the step part of the loop by and J will be add together. And so in I, and this is the conditional branch part of the instruction. If the AI is not equal to the J, then we should jump to the loop. Otherwise we go to the next instruction and we will move out from this loop structure. So there is a loop here until this condition is not satisfied. But this is not the perfect way that we can implement the previous high-level language into the MIPS. If we show you another example, we have a wireless structure in the high-level language while a indexed AI is equal to the variable k. I want to perform this statement. I will be add together and stored in the AI. So again, first you have to compute a index 1 to this point and then check it a instead of check this. Equality. As you can see, we check the reverse condition or the complement condition if they are not equal. If a index IE is not equal to the k. Hey. Index is here. K is here. If they are not equal, go to the exit. Come out from the wide. Otherwise, the body of the wall will be executed. And in this example, I'm JB. And then again, come back to the Y condition. Jump to the loop. So this condition of the loop is computed. First, we have to find the aims. And then we should check this condition. So all of this part is the checking of this condition. A index 2 is equal to the k or not. But in a sort of state that if they are equal, continue in assembly. We mention the men because we can say that when to jump out when the condition is not true. So do not jump out and continue the loop because this condition is not satisfied. And jump back to the loop. Every time in high level when this statement is finished, they come back to this point and check the condition again and again. And it will be continue until this condition is not satisfied here. This job moves back to the square. So how many statements we have here? 1, 2, 3, 4, 5, 6, 7 statements. We have one entry and one exit from here. I can write it in better way. Let me show you. This is the flow chart of this condition. This statement. We check the condition, and then we say that if it is not equal, go to exit. Otherwise, we perform the body and come back and check the condition again. Another way of implementing this new structure in assembly is in this format. First, write the body of the loop and then the condition if it is to come back to the body. And if it is not to go out. And in the beginning, we jump to this location. Let me show you. First here in the when we enter to this location, we automatically jump to the condition. Here we compute the condition. And this time we say that if they are equal, a index 1 and k are equal. Come to the loop and perform the I equal plus j and do it again. So now the previous code is written by 6 statements. 1, 2, 3, 4, 5, 6. The first one is outside of the loop. Only execute 1 times, but the body of the loop is these 6 statements. But in the previous implementation, all of these parts are inside the loop. 1, 2, 3, 4, 5, 6, 7, 16. So we reduce one instruction and this implementation improves the previous one. So there are 2 ways to implement a loop structure in a segment by checking the condition or the complement of that condition. Till now, we only check the equality or not equality. We compare two elements, and according to the equality or not equality, we will jump to another statement. But there are some other conditional expression like less than, less than, or equal. Greater than or equal, but are useful to build their conditional expression in level language. How we can implement them in MIPS. This type of compare statement cannot be converted into one statement. In MIPS, we have to split it into two sections. We have a specific set instruction which set the value of the register to 1. If one condition is satisfied, for example, set less than compare the content of the just 16 and 17. In this example, if register 16 is less than the register 17, then the register 1 will be set to 1. Otherwise it will be set to 0. So in order to check it, f is less than g. I think that the f and g are inside $10, 16, and 17. We should first perform this condition, set less than set the register 1 to 1. If this condition is to otherwise set it to 0, then by using branch not equal, we can compare the content of this register and the 0 register. As I mentioned, 0 register always have the value of 0. So it is hardwired to 0, so you cannot change it. So if the result is not equal to the 0, it means that it is less. You think that this condition is true? So this is the way that we implement this line in MIPS. We want to jump to the left label. If this condition is satisfied, f is less than g, whereas compare f and g, and the result will be inside the register 1. If this condition is true, this register is 1. If this condition is false, this register is 0. Then the check here is at 0 or 1. By compare it by branch not equal. This result register and 0 register. If they are not equal, it means that this condition is satisfied. And we jump to the list. Enter text you wish spoken here.